So thank you everybody for joining this morning. So we are Queen's Hyperloop design team. So I am Matt Burchard. I'm the mechanical director of design on Queen's Hyperloop, and I'm joined by Sam and Arshad. Sam is the propulsion lead, and Arshad is the suspension lead. So go to the next slide.
Oh, sorry about that.
So as mentioned earlier, we'll be presenting the suspension and propulsion. So suspension will be presented by Arshad and propulsion by Sam. We'll get into it.
Hey everyone, my name is Arshad and I'm a second year mechanical engineering student. As mentioned previously, I am also the suspension and levitation manager for the Queen's Hyperloop design team. Now with that being said, the following slides are intended to give everyone an insight on what we've been working on, as well as some plans for moving forward. So starting things off, we have an image of the full suspension system of our previous design here at the bottom of the slide. It featured an adjustable alignment system, which allowed the side wheels to move to better fit onto the track. In terms of shock absorption, well, as you can see, there were none in the previous design. This caused vibrational instability due to track imperfections. Finally, tighter tolerances will be used to prevent loose and shaky parts, which were present on the previous design caused by poor bearings. While the design was good for the time, it definitely needed some improvements. So for objectives and focus for this year, it begins with optimization. The current design features an integrated side and bottom wheel assembly, which saves on weight, materials, and cost. Further optimization will be done on parts to ensure they are designed to endure all the forces being applied onto them. In terms of adjustability, we built on the outgoing design's capability by implementing a spring, which allows us to add pressure on the wheels for preload forces. This new adjustable alignment system enables us to alter the normal forces felt by the drive wheels, which leads to both increased grip and more wheel travel. Another major improvement made for the current design was the addition of coil shocks in conjunction with bushings and wheel coatings. The coil shocks are used to dampen vibrations, primarily caused by track imperfections. We will also be focusing on manufacturing by building the majority of the parts needed as opposed to outsourcing them. We will be building custom shafts in order to reduce play within bearings to ultimately ensure tighter tolerances. Furthermore, physical testing will be done to look at load cases through the use of strain gauges. We'll be developing both nominal and proof testing to determine whether or not the components we currently have are up to spec. And finally, in the background, throughout the year, we'll be conducting research and looking into viable methods of levitation, such as magnetic levitation and planar air bearings. We're also looking into various materials and newer manufacturing processes, which includes designing and building carbon wheels. As far as the timeline goes for this year, we're currently working on finalizing our load cases and completing all required FEA using both SolidWorks and ANSYS. We'll soon be moving into completing our bill of materials and begin to manufacture our parts in-house or order some if necessary. Going into the new year, we're starting off with building and assembling our design. Further physical testing will also be undertaken at this stage. Once the system is built, minor revisions and final iterations will be done to ensure the pod is competition ready.
All right, thanks, Arshad. Hello, everyone. I would first like to thank CHC for hosting this showcase. It's been very informative so far. I'm Sam Williamson. I'm the propulsion manager for the Queen's Hyperloop design team and a third-year mechanical engineering student. For those who may not be familiar with our terminology, the propulsion subsystem consists of the drive system, so think of the motors, gearbox, and wheels, and the liquid cooling system for those motors. Today I'm going to discuss our previous propulsion design and its drawbacks, as well as our new design. Our previous design used 4 Scorpion motors, all connected to one gearbox, which in turn drove our drive chain. This then drove our wheels. The first issue that many of you will notice right away are these wheels. They were originally motorcycle wheels and rode on the bed of the track from the previous competition. They have a very large moment of inertia and are very soft. However, they were simple to implement. The previous pod also had a drive chain which could vibrate at certain speeds, and is less safe even when covered with a shield that was removed for the picture. Lastly, this pod had no active liquid cooling for the motors. This wasn't the limiting factor for the pod's performance, so it wasn't something to worry about for that design. Our new drive system uses a completely different design. There are only two gears involved, the drive gear, which is on the same shaft as the motors, and the driven gear, which is on the same shaft as the wheels. The system you see here is replicated on the back of the pod for a total of 4 motors and 4 wheels. A portion of the gearbox is transparent, so you can see the gears themselves. For this design, we were working with DHX machines, and we'll be incorporating their Peregrine P40 motors into our pod. At over 50 horsepower per motor at 450 amps, they deliver more than enough power. To determine the optimal gear ratio for a drive system, we created a MATLAB simulation. This simulation tests the pod's performance with gear ratios from 1 to 10 up to 7 to 10. It was determined that for any track over 2.43 kilometers, a gear ratio of 4 to 10 or 2 to 5 allowed the pod to go the distance the fastest. For a 10-kilometer track, the pod would only take 87 seconds. With this gear ratio, the pod can accelerate from 0 to 450 kilometers an hour in 16 seconds in a vacuum with a peak acceleration of 8.5 meters per second squared. The entire drive system pivots around one point that's hidden in this field of view. This allows us to use preloaded shocks to stay secure to the track. Our gearbox and wheels will be custom fabricated, and we are currently looking into partnering with Markforged for acquiring continuous fiber 3D printed parts made from their proprietary composite materials. To be able to run such powerful motors for any useful amount of time, they need to be kept cool. For this, we needed to develop a dielectric liquid cooling system from scratch. Cooling in a vacuum is difficult because convectional cooling is the most accessible way of cooling heat, and there is ideally no air in the tube. Conductive cooling wouldn't work very well. Conductive cooling would not work very well because that would involve rubbing against the track for the whole duration. Because of this, the sum of a few methods of cooling are used to cool the motors enough. First, the motors are cooled by storing the heat in the dielectric coolant, which has a heat capacity close to that of water. Second, copper tubing is run along the side of the composite shell to transfer heat into it. Next, the warm shell will radiate heat to its surroundings and participate in some residual convective cooling. Additionally, the cooling system components are mounted away from the main chassis to help radiate that heat as much as possible. The tanks have a pressure relief system set at 15 psi to avoid overpressurizing the system. The tanks are placed at the low pressure side of the pump because the head on the high side of the pump will be greater than 15 psi. To summarize, the loop is replicated once for each motor for a total of 4 pumps, which you can see in orange, 4 coolant tanks, which you can see in blue, and 4 sections of copper tuning that line the shell. As this fall term comes to an end, we are finishing up the SolidWorks CAD and the braking portion of the MATLAB simulation, as well as acquiring parts. For this, we'll be sending some files to machine shops for custom fabrication. Once we have some parts, we can begin construction. The winter term will consist of completing the failure modes and effects analysis and writing our technical report for CHC while finishing construction. Once we have it assembled, we will start testing on a dyno that we are working on. Then, we'll be doing some adjustments and fine-tuning to get ready for the competition in June. Thank you all for listening. Do you have any questions?
If you have any questions from the audience, you can go ahead and unmute your mic or type it in the chat.
All right, well, thank you everyone for listening. I guess we'll be here for a little bit longer if anyone has any questions.
Yeah, thank you, Queen's Hyperloop. That was a great presentation.
Thanks for having us.
Thank you.